let's continue our foray, our journey into organic chemistry. We were just talking about hydrocarbons, right? Well, hydrocarbons, while they can react with things, most of the functionality that comes from hydrocarbon chemistry or organic chemistry comes in the form of functional groups. And that's what we'll be talking about today. So the functional groups that we'll be talking about today are the hydroxyls, the ethers, and the thiols, right? Hydroxyls are alcohols, right? They're also known as alcohols, and they're called hydroxyl groups because they have this OH, right? That's the hydroxyl functional group. It has an OH on it. It looks very similar to the hydroxide ion from it's like sodium hydroxide, except that the hydroxide ion has a negative charge, right? Because it's an ion, but a hydroxyl group it does not have a charge at all, right? It actually is not ionic bond to anything, right? It is a covalent bond to a carbon, so that's why it doesn't have a charge, like an overall charge, like hydroxide. So a very common, very common hydroxyl or alcohol uh, molecule is methanol, right? Another one is also a phenol, right? The phenol here is actually made of a benzene ring, right? And when it's just a benzene ring by itself, another name of it is called phenyl group or a phenyl, right? But when you add on the hydroxyl to it, it becomes phenol. I'm getting a little messy here, so let me erase this real quick and we'll talk about ethers. So ethers they contain an oxygen in the center, right? And they're singly bonded, like so, singly bonded, right, to two carbon groups on either side of the oxygen, right? So a very common ether is this. It's actually called ether, right? Where it's an oxygen in the center with a single bond to a methyl on one side and a single bond to a methyl on the other side, right? Another name for that is actually dimethyl ether, because it has two methyl groups in it, so dimethyl ether. And then last on this particular slide is called a thiol. Some old school people call it the sulfohydryl group, but in modern times we call it, or IUPAC, we call it thiol. And a thiol, it looks just like a hydroxyl, except instead of OH, it's an SH. And that works out pretty well, pretty similarly, right? Because sulfur and oxygen are in the same group in the periodic table, right? So I think sulfur is right under it. And so a very common one here is ethyl thiol, right? And there's the SH for the thiol, right? And then so at the bottom here we have ball and stick drawings for methanol, right? Phenol, ethyl thiol. I think some people actually call it ethane thiol too. And then dimethyl ether, which you can't see because my head's blocking it. I'll close my head briefly for you to be able to see that. Yeah, dimethyl ether, right? So how do we name alcohols, right? Very simple, actually. There's the IUPAC name, and then there's the common name, right? IUPAC means methanol, which is just a CH4, right? One methyl group, and an alcohol. So we saw that right here. That's methanol, right? Its common name is methyl alcohol. Drinking alcohol, on the other hand, is CH3CH2OH, right? Very similar to ethyl thiol, but since it has a hydroxyl group in it, it's called ethyl alcohol. That's drinking alcohol, right? Or the IUPAC name for it is ethanol, right? So naming alcohols, those simple alkyl alcohols, is pretty simple, right? Let me bring myself back. So let's practice naming some alcohols. All right, let's practice naming some alcohols. So naming alcohols is pretty easy. All you have to really do is number your hydrocarbon from the alcohol, starting with the alcohol, right, or starting on the end with the alcohol, and then at each position name what's actually there. So, for example, the alcohol is on the right end, right, of the of this molecule. So we'll start it as one, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6, right? So 6 carbons there, right? On carbon 2, there's the alcohol. And then on carbon 5, there's a methyl group, right? So very simply, this molecule is 5-methyl 2, and then remember what we do with alcohols, we end them in "ol", right? Like methanol or ethanol, right? So this is 6 carbons, so that's hexanol. Right? Pretty simple. Let's do that again with this next one. It's this almost the same thing, except only now there's only 5 carbons. Whoops. There we go. 5 carbons. The alcohol or the hydroxyl group is on number 2, and then the methyl group is on number 4. So quite simply, what is this one? It is methyl. Oops, forgot my hyphen. Methyl, 4-methyl 2. Now it's 5 carbons, so it's pentanol. Kind of like pentane, 5 carbons, except with an alcohol, so it's pentanol, right? And then we have this benzene ring here, right? And has an OH on it, which makes it a what? A phenol, right? But again, we always start where the carbon is, the hydroxyl's connected, right? So 1 carbon there, 2 carbon, 3 carbon, 4 carbon, 5 carbon, 6 carbon, right? So this is quite simply named 3 because the bromine or the bromo the bromo functional group is attached to the 3rd carbon. So 3 bromo. And then what's the rest of this thing called? The rest of it is a phenol. So 3 bromophenol. So naming those guys are pretty simple. For alcohols. Next, let's talk about some thiols. So thiols contain sulfur, like we talked about before, right? And that sulfur is within this functional group known as a thiol group, SH group. Again, I was saying before, some older people call it the sulfhydryl group. I really doubt that I spelled that correctly, but oh, you know what? I think it's actually L-Y. Hydro? Or no, or... Sorry, Y-L. Yeah, that's actually, I think that's how you spell it. But only old people spell it that, use that phrase. So I expect you to know the thiols, that they're thiols when they have an SH group, right? Now this is an understatement right here. It says often strong and sometimes disagreeable odors. Not just disagreeable, they just outright stink. My old boss, actually, my old boss's boss, right, was a guy named Mo Cleland, and Mo Cleland invented this thing called Cleland's reagent, right? And literally, Cleland's reagent, it had, I think it had 2 sulfurs in it, and holy mother. It smelled like burnt butthole. Like it was really, really bad. So think about 2 sulfurs, right? That's sulfur. Just sulfur when it's covalently bonded in a hydrocarbon just smells really bad, right? Because I've had sulfur powder out before and it doesn't smell like anything, right? So it just smells really bad. So they're found in cheese, onion, garlic, oysters. They're used to detect gas leaks. So that's another thing to be take note of there. Um, a lot of people think that the smell that they smell coming from uh, like the natural gas from your stove, like your range and stuff like that, it comes from the methane. It actually doesn't come from that. It comes from sulfide gas, hydrogen sulfide gas, and it smells really bad. Yeah, so that's how you smell it. Methane actually doesn't have a smell at all. The same goes with. Oh, by the way, if you don't know what that is, yeah, hydrogen sulfide gas is H2S. Um, Same goes with like flatulence, for example, right? I mean, there's a lot of people think that it's methane in flatulence that smells bad, but it's those sulfur-containing, uh, hydrogen sulfide gas molecules that are being produced by the bacteria in your gut that make that smell, and that's what you're actually smelling, right? So, oh, another thing that smells pretty bad is the smell of a skunk spray, right? The, the smell of skunk spray is actually it's from a chemical compound called trans 2-butene 1-thiol, right? Notice here, this is calling back to things that we've learned in the past, right? This is a trans, right? Because the thiol is on opposite ends of that methyl group right there. It's a trans, okay? And then right here, 2-butene, right? Because the butene, which is the double bond part, right here, begins at the second carbon, right? Because that's carbon 1, carbon 2, carbon 3, carbon 4, right? And then it's 1-thiol right here because the thiol is connected to the first carbon, right? See, so we're bringing it all together when it comes to naming organic compounds, and you can see that when IUPAC names things, it's pretty simple. It's really just you number the number of carbons, and then each functional group or substituent group is numbered where they are on the carbon chain, right? Pretty simple. What is next? What is next? Oh, naming thiols. We just named one here. Let's name a few more, right? So again, we have here methanol, right? When an OH is connected to the just a methyl group, they're just using that as an example because it's the same thing when you do the SH, which is the thiol right here, right? So methane thiol, right, which is a methyl group connected to a thiol group, right? Ethane thiol, which I called ethyl thiol earlier, but ethane thiol, same thing, right? 2 carbons. Remember, ethyl means 2. Eth means 2. And then 2-butane thiol, right? 2-butane thiol. Pretty simply because carbon 1, 2, 3, 4. It's there on the second, the thiol's there on the second carbon, and that's why it's 2-butane thiol, right? Because it tells you where the thiol is. So we see methyl thiol or methane thiol here in oysters and cheese. So there's a picture of some oyster and cheese. Onions is 1-propane thiol, right? That's the smell coming from onions. And then garlic is 2-propene thiol, 2-propene 1-thiol, right? Makes sense. Makes a lot of sense. So naming thiols is very similar to naming alcohols. Next, we'll talk about some. There we go. Next, we'll talk about some ethers. Again, an ether is an oxygen connected in between by single bonds to 2 carbon groups, right? They're either alkyls or aromatic rings, right? Alkyl like a hydrocarbon, methyl, ethyl, whatever, right? Or aromatic rings like phenols, right? Or benzene rings, right? So here, we saw this earlier where it only called it ether, but its real name is actually dimethyl ether. But when you go to the lab and you work in the lab and you say you want ether, that's usually what people will bring you because it's kind of like the common name for it, right? And then here's the ball and stick for diethyl ether right here, right? They have a bent structure, like water and alcohols do, which makes sense because the oxygen is there, right? And it's on both sides. There's the two bonds on both sides, but they're being pushed down by the two lone pairs, right? That are also oxygen there, much like in water. Okay. Has common names given to the alkyl names of the attached groups, followed by ether, right? So in this particular molecule right here, we have a methyl group at the front of this ether right here. And then we have the propyl group attached here, 3 carbons, so that's a propyl group right here, right? So literally it's named methyl propyl ether. So basically what they're doing there is they have put the methyl, since it's at the beginning of the molecule, and it's the smallest part at the beginning of the name, and then on the other side of the oxygen is the propyl, so that's why they called it propyl, and then ether, to say it's an ether, right? Some other names for some ether groups. We have fluorane or isofluorane right here, right? This ether, the oxygen is right there in the center, and it's connected to these fluorine moieties. And then we have influorane, or also known as ethyrane, right? Suprane, or desifrane, fluorine. And then sevofluorane. And those are just other ether compounds. You don't really need to memorize those, but they're just other common ether compounds. So we can classify alcohols as either primary, secondary, or tertiary. What's the difference? Well, in a primary alcohol, there's only one methyl group. The rest are hydrogens, and the hydroxyl is connected to that primary carbon, right? So that makes it a primary alcohol. In a secondary alcohol, there are 2 methyl groups connected to that carbon that the alcohol is attached to. This is 2-propanol, right? Because it's on the second carbon. That makes it a secondary alcohol. And then a tertiary alcohol, there are 3 methyl groups attached to that center carbon, along with the OH, making it 2-methyl 2-propanol, right? 2-methyl 2-propanol. And since there's 3 methyl groups, it's a tertiary alcohol, right? So yes, we can classify alcohols as either primary, secondary, or tertiary, and that has implications on what kind of reactions what kind of reactions these alcohols can actually participate in, right? But before we can talk about reactions of alcohol, let's talk about how soluble it is in water, because most reactions happen in water, right? In life, especially. So I think I talked about this a little while ago, right? Where an OH group is partially polar, right? And so that makes it soluble in water. I mean, that's how you're able to get like beer, because ethanol is dissolved in the water, and beer is only like 7% ethanol, right? Or on a more extreme case, Everclear, right? Which is 95% ethanol, right? And it's dissolved in water because there's 5% water left, right? Or maybe the water is dissolved in the ethanol. Anyway, right? So how does it dissolve in water? Well, we recall that the water looks like this up here, right? In the upper right-hand corner. The partial positives are in the hydrogens. The partial negative is in the oxygen, right? Giving it a polar, giving it polarity. There it is. I was like polarity, giving it polarity, right? And then what can happen then is that the ethanol group, or the alcohol group on the methanol, or ethanol, whatever, but in this example it's methanol, also has the same partial negative on the oxygen and partial positive on the hydrogen. So water molecules can surround it just like it can surround an ion. Right? Just like it can surround an ion. With the partially negative oxygen liking the partially positive hydrogen from the ethanol or methanol, or the partially positive hydrogen from the water being attracted to the partially negative, electronegative oxygen from the methanol. Right? The key, though, is that as you get more and more and more ethyl groups, as the alkyl group gets longer and longer and longer, right, the less soluble it will be in water, because that part isn't soluble in water, the alkyl chain, the hydrocarbon chain. So when it's just an ethyl, like this is ethanol right here. The example up here is methanol. The example down here is ethanol, right? Ethanol, because of the OH, is soluble in water, even though the ethyl group is a nonpolar carbon chain. But the polarity of the hydroxyl overpowers that, and so that's why it can be dissolved in water. But you get out to 1, 2, 3, 4, 5, 6, 7, 8. So that's octane, or we can call it octanol. It gets a little bit harder for it to dissolve in water, even though it has this polar hydroxyl group there. Okay? So as the number of carbons increase, the less likely it is to be soluble in water. Surely I have a chart to show you. Surely. Yes, I do. So here we are with methanol. It has 2 carbons. Ethanol, 2 carbons. Methanol with 1 carbon. Ethanol with 2 carbons. They're both soluble. 1-propanol is still soluble, right? But then we get to butanol, 4 carbons, not soluble, slightly soluble, right? But then once you get to 5 carbons, that's where the breaking point is. 5 carbons, it is considered insoluble in water, right? Remember that. Remember that. So let's talk a little bit about the solubility of then phenols, right? Phenols are slightly soluble in water, right? Because of the OH group. Remember, I was telling you last lecture, I think it was, about chloroform phenol extractions of DNA. It's what they use in forensic science and in molecular biology to extract DNA from cells, separate it from things like proteins and stuff like that, and other cellular debris, right? Because all the proteins and the cellular debris and all that stuff will stay in the phenol layer, the chloroform layer, the organic layer, basically. And DNA is actually very soluble in water, and so it stays in the water layer, right? And I may have just gone beyond the scope of the class, but let's keep going. So the hydroxyl group can form hydrogen bonds with the water molecules, just like in the last example, right? And when it does that, it can actually be used as it can actually do acid-base chemistry, right? So here's your water, which is your base, and then your phenol here, right, is your acid. And then when they combine with each other, I'm going to do something crazy here, so don't get confused, right? The 2 lone pairs on the the water will come take this proton, or this hydrogen, right, from the oxygen, I'm going to expand this out so you can actually see the bond here. This is what it actually looks like in there, right? The bond is just missing. Okay. And so when my arrow goes and takes that hydrogen, the electrons from this single bond go into the oxygen, giving the oxygen one negative net charge. Right here, see? One negative net charge. And since we took a proton, or a hydrogen plus, right, from the hydroxyl of the phenol and gave it to the base, the water, that's why we get H3O plus here. So if you remember from your acid-base chemistry, if this is the acid, right, then this is what? A conjugate base. And if this is the base, the water is the base, then that is what? The conjugate acid. If I could spell conjugate correctly. Conjugate acid. Right? And since phenol is not a strong acid, it has definitely got some equilibrium going on here. Right? We don't know exactly what, but it does. It definitely does. Okay? See, we have things that are really considered acid-base general chemistry happening in organic chemistry, which is something that you need to be aware of, right? Something that you need to be definitely aware of. Oh, and the other thing to notice too is that normally you see OH right here, right? You see OH, and when we were talking about acid-base chemistry in the previous lectures, OH is generally thought of as a base because it's about part of sodium hydroxide, and sodium hydroxide is a really strong base. But here it's not hydroxide; it's hydroxyl, right? And then as a hydroxyl, it actually acts more as an acid because it donates protons to water, right? Makes sense. They were once used as antiseptics, although I don't know if you would want to use phenol as an antiseptic. It's a little bit nasty. Smells weird, right? So, let's talk about a few reactions of alcohol here. Some reactions of alcohol. You can do a dehydration reaction with alcohol where you heat it with an acid catalyst. And when you do that, heat it with an acid catalyst, right? This is the alcohol right here, right? There's your OH sitting right there, right? There's your OH sitting right there. You heat it with some acid. Wow, that's funny. I've been watching this show on Netflix called Luke Cage, and I'm a huge Marvel MCU fan, of course. And I just realized that the reaction that guy, oh man, I can't remember the scientist's name. Anyway, the reaction that guy used with Luke Cage, into that bath or whatever it was heat and acid. Don't worry, that wasn't a spoiler or anything like that, but it seems pretty simple. So to be creating a superhero like Luke Cage. Anyway, although he doesn't consider himself a superhero. In this reaction, though, with the heat and the acid, what happens? Well, it's called dehydration reaction because you lose the water from the molecule, right? The H from here and the OH from here combine with each other to make a water, and now you have an alkene instead of an alcohol, right? An alkene and a water. So just remember that if you have an alcohol and you treat it with acid and heat, you'll always get an alkene, right? And a water. So oxidation reactions also occur with alcohols, specifically the oxidation of a primary alcohol, right? Here we have a primary alcohol connected to this first carbon right here, right? The primary alcohol. It gets oxidized, And when it gets oxidized, we lose the hydrogen, and this becomes a double bond. Which makes sense, right? Because when you oxidize something, you're losing electrons. And when you lose electrons, you don't have enough to make single bonds anymore, so you have to make double bonds, right? To share more electrons. So you go from a primary alcohol to an aldehyde. This reaction can actually keep on going, right, and get oxidized again, and then become a carboxylic acid, right? Right? And oxygen gets inserted right there between that carbon and that hydrogen. So one of the rule of thumbs that you have is that whenever an oxidation happens, you'll either lose electrons, right, or you'll have oxygen added to the molecule some way. And then whenever you reduce things, you'll lose oxygens, right, and then you'll gain probably hydrogens, right, or more electrons, right? That's a kind of a rule of thumb there. So just remember, primary alcohol gets oxidized and becomes an aldehyde, right? And then that aldehyde can go on and become a carboxylic acid, which is that guy right there. We'll talk a lot about carboxylic acids in a second. Okay? Carboxylic acids are part of like fats and stuff like that, right? So you can also oxidize a secondary alcohol. Here you have your secondary alcohol, right? There it is, that center carbon right there, with two methyl groups around it. This O in brackets here that means oxidizing, right? Some kind of oxidizing agent, oxidizer. And when you treat a secondary alcohol with an oxidizer, you get a ketone, right? You get a ketone. So a ketone is basically, and we'll talk about this more in a little bit, a ketone looks like this. All ketones have a double bonded oxygen to a carbon, and then on either side of the carbon is some alkyl group or some functional group or something, right? One of my old bosses used to call R groups and name them as rest of the molecule. Oops. Rest of molecule. Molecular? No. There we go. Rest of the molecule. God dang it. It looks really bad on the screen. Let me write that out again. Rest of the molecule. That doesn't look right either. I'm gonna start over. Here we go. Rest of the molecule. Now you really think these, Apple pencils are supposed to work really well, but sometimes they don't. But if you ever see an R on anything, that's what it stands for. Colloquially, rest of the molecule. Could be anything, right? And a ketone is basically an oxygen double bonded to carbon with the rest of the molecule on either side. Okay. We can also, by the way, if you're wondering, forgot. If you're wondering, you actually can't oxidize a tertiary alcohol. So you don't have to worry about that. I'm sure you were all wondering about that, like with bated breath. What about the tertiary alcohol? Well, I'm here to tell you that it cannot get oxidized, right? No oxidize, right? No oxidation. Don't have to remember that one. All right. Next, we're going to talk about some oxidations or reactions of thiols, right? Oxidations of thiols. So this is that molecule I was talking about before with the sulfur groups, right? Also known as the sulfohydryl groups, right? Most commonly, you'll see them as a disulfide, okay? And they're used to cross-link proteins together, right? They'll be used to cross-link proteins together. Most proteins are held together by their tertiary structures, or the big 3D structures of proteins, are held together by non-covalent interactions. One of the covalent interactions that holds them together is called the disulfide bond, right? So here you have a protein chain, and you have another protein chain. Okay, and this could be any one of two different amino acids, right? Actually, I think it's just one amino acid, cysteine. Yeah, cysteine. I mean that. Sorry, let me rephrase. I think that you only need to know one of those amino acids, and it's cysteine. And cysteine has the CH2, right, connected to the rest of the molecule, which is that protein chain, and then which is cysteine and the rest of the protein chain, and then has a thiol group at the end of the chain. And so when you get two protein chains with two cysteines that are exposed, right, they can get oxidized, where you lose the hydrogens, and the two cysteines get bonded together to form a disulfide bond. Right? The hydrogens that were there go into the water, go into making water, right? And now you have a protein chain, two protein chains that are connected by disulfide bond. And we'll talk about that a lot in the proteins and amino acids and stuff section of our class, right? A lot. And then I would be remiss in my duties if I don't talk about some health effects and links to life when we talk about alcohols and thiols and such, right? One of the most important alcohols in all of our lives, right, is ethyl alcohol or drinking alcohol. How do we make that? Well, it's just glucose, and it goes through alcohol fermentation with yeast, right? You could use any kind of yeast, actually. It doesn't have to be any special yeast. Bread making yeast is just as good, except that my mother-in-law tried to make some bread a couple weeks ago, and the yeast was like 14 years old, and we've been watching a lot of British baking show, and they use the word stodgy. And let me just tell you, the bread that she made with that 14-year-old yeast was definitely stodgy. Anyway, in the reaction though, we ferment. We do alcohol fermentation, and we use glucose as the source and the food source for the yeast, and we get ethanol, which is drinking alcohol, and carbon dioxide, right? So that's how you actually make beer, right? That's why beer gets fizzy, because of that carbon dioxide, and it has 7% alcohol in it, right? You can also make alcohol too by doing a reaction with ethene, right, and water, and then you can also make ethanol too. But I wouldn't drink that because it's purely organic synthesis, and you never really know. It might make you go blind. We'll go over why in a minute, right? So that's alcohols, right? We were talking about phenols before, right? And here we have vanillin, right? Which actually is the flavoring chemical of vanilla, right? We have eugenol, and we have isoeugenol right here. They're both flavoring agents as well. Can you see the difference between the two? Remember what iso means. Iso means it's the same molecular formula but differently connected, right? And you look real closely right here, the eugenol has the double bond there, and then the isoeugenol has the double bond there, right? And then we have thymol. That's another flavoring, right? I wonder if that's the flavor that comes from thyme. I'm not really a good chef, so I don't know. Someone look that up. Is that where thymol comes from? I'm not sure. Another important alcohol in our lives is this one. This is an alcohol called glycerol. The IUPAC name is actually 1,2,3 propane triol. Right, propane triol. And you see this when you make soaps, because fatty acids have have carboxylic acids in it I was talking about, right? And then you can make soap out of fatty acids, and then one of the byproducts is glycerol. Um, it also make uh, biofuels. Biofuels come from fats as well, and then in that reaction, the product you get is a fatty acid methyl ester, which we'll talk about later, and glycerol. Right, so glycerol is it's very thick and viscous and clear, right, and you'll know it when you see it. Another interesting one in our lives is this one. It's ethylene glycol. So ethylene glycol is actually an antifreeze, right? Super toxic. I think it's used in solvents too for paint and ink and such, but it's definitely toxic. Don't drink that stuff. Don't drink that stuff. And last but not least, this is bisphenol A. And if you've ever been worried about bisphenol A. If you've ever been worried about the plastic in your water bottles leaching chemicals from the production process because you've had it sitting out in the car for too long, or you're washing it in hot water with soap and such, the thing that you're worried about is this. It's bisphenol A, right? It's used in the making of a plastic called polycarbonate, PC, polycarbonate, and when you leave it in heat for too long, or you wash it with detergent and such, the plastic, the polycarbonate, bisphenol A can leach out in very, 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 very small quantities. That's why people started started moving away from water bottles and started, filling up their tumblers and their turbines and water filling stations and such, right? Yes. And then some more about methanol poisoning, because we were just talking about don't drink some of these methanols. One of the things that's very, very bad to drink is methanol, which is funny because methanol looks like this, right? Ethanol looks like this. No, that's wrong right there. Let me try that again. There we go. Right, so this is methanol. And this is ethanol. Right? You can drink ethanol and have a good time. Not too much, but you can have a good time. But if you drink this, you might go blind. You might die. Why is that? Well, because in your body, there's enzymes called dehydrogenases, right? Dehydrogenases. And they go through and they convert methyl alcohol or methanol into formaldehyde. I don't know if you knew this. I mean, you probably have, but like whenever you see those jars of dead animals specimens, they're in some kind of liquid, right? That liquid is formaldehyde, right? It keeps things from growing in it, like bacteria and such, because it's that deadly. You definitely don't want this stuff to be made inside your body. No formaldehyde. And it gets even worse. It can be even further oxidized and become formic acid in your body, right? All right. So make sure you are not drinking methanol, right? It is not a substitute for ethanol, because you can't drink ethanol. Speaking of ethanol or drinking alcohol, right? Again, I'd be remiss in my duties teaching this allied health class if I didn't talk about the health effects or the bodily effects of drinking alcohol. It acts as a depressant, right? And it kills or disables more people than any other drug, probably due to car accidents, right? Drunk driving and such. When it's in your body, it begins as ethanol. Those dehydrogenases get a hold of it and turn it into acetaldehyde, right? Which, by the way, is not as deadly as formaldehyde, right? Can you believe that? Just one carbon, one methyl group is the difference between killing you when you drink it and not killing you, right? But you can still die from alcohol poisoning, right? And that can get more oxidized and become carbon dioxide in water, right? You got to use a breathalyzer to see what someone's blood alcohol level is, right? But just as I guess for context, ethanol metabolized by a social drinker is metabolized by those dehydrogenases I was speaking of, right? Alcohol dehydrogenase to be exact, at a rate of 12 to 15 milligrams per deciliter per hour, right? For a social drinker. An alcoholic, though, right, can actually metabolize that at a rate double, 30 milligrams per deciliter per hour. And that's the reason why an alcoholic can drink more alcohol and not be as affected. Right? So let's break this down into something practical, right? If you have one 12-ounce beer or a glass of wine in 1 hour, your blood alcohol could be at 0.025. What's the behavior? How's that going to affect you practically? You're going to be slightly dizzy, more talkative. More talkative. Let's put 2 beers in you, right? 2 beers in you makes it 0.05. You're getting very close to Texas's blood alcohol limit, right? I think Texas blood alcohol limit is 0.08. Here you feel euphoria, you start talking super loud, and you laugh at everything, right? At 4, though, that's when things go bad. Your blood alcohol can be around 0.1, which is above the legal limit. There's a loss of inhibition, loss of coordination, it causes drowsiness, and again, like I was saying, it's legally intoxicated in most states, right? At 8 drinks, 8 beers in 1 hour, 0.2 blood alcohol. You're intoxicated, obviously, very quick to anger, and you have a very exaggerated emotions, right? I don't think that's everybody, but they're trying to teach you something here in this textbook, I guess. And then at 16, you're at 0.3 blood alcohol level, and you're unconscious. I guess the term is blackout drunk, right? And then 16 to 20, wow, that's a lot of beers. 20 beers in 1 hour, holy mother. You're at 0.5, and you're probably in a coma or you're close to dying. So be careful. So before we can talk about aldehydes and ketones, we have to talk about the carbonyl functional group. The carbonyl functional group is quite literally an oxygen connected to a carbon with a double bond, right? This oxygen has 2 lone pairs at the top, as all oxygens do when they're connected to something with a double bond, right? And so what happens is that the oxygen is already electronegative. You know that from previous lectures, right? It's already electronegative. What that means then is that it draws electron density away from this carbon right here, right? It draws electron density away from the carbon. That's why the oxygen is partially negative and the carbon is partially positive, because the electronegative oxygen is drawing electron density away from the carbon, right? That means then that this carbon is just dying for some electrons, and so we can call this carbon an electrophile. Right? And what can happen is that another molecule, like a nucleophile, right, can attack that carbon. So that carbonyl makes up the bulk of what is considered an aldehyde or a ketone, right? So here's your carbonyl group at the top with a partially negative oxygen, partially positive carbon, right? And the carbonyl group can become an aldehyde, which is this guy right here, this functional group. An aldehyde is always a carbonyl group with a hydrogen, right? And then this part here can always like be an R, like the rest of the molecule. In this case, the R is a methyl group, and when the R is a methyl group, it's called aldehyde, right? On the other hand, though, if the carbonyl group has R's on both sides, and in this case, those two R's are methyl groups, right here, one methyl group here, one methyl group here, it's called a ketone, right? It's called a ketone. So you just have to remember that if there's an H there, right? If there's an H there, a hydrogen there, it's an aldehyde when it's connected to a carbonyl. But when there's something other than an H attached on both sides of the carbonyl, then it's a ketone, right? We usually write aldehydes as CHO, right? And then we usually write, for shorthand, we usually write ketones as CO. So here's aldehyde drawn as a line angle formula, right? And here's a ketone drawn as a line angle formula, right? So let's name some aldehydes now. It's pretty easy to name an aldehyde with IUPAC standards. You just change the E at the end to Al. So for example, here we have methanal for 1 carbon, ethanal for 2 carbons, propanal for 3, and butanal for 4 carbons, right? It's a little bit different with the common names here for the aldehydes. When you have 1 carbon, it's a form, so that's formaldehyde. Remember formaldehyde, that's a thing that we put dead specimens in so they don't grow bacteria and nastiness over time, that nasty liquid. Also the thing that methanol gets turned into when you drink it, right, with the dehydrogenases, and then you die or you get blind or whatever. So remember that. If there's 2 carbons, it's acete, like acetaldehyde, right? Acetaldehyde is that is again the molecule that ethanol gets turned into by the dehydrogenases in your liver, and so that's why you can drink it. It's not as deadly, right? 3 carbons is propion, so propion aldehyde, right? Propion aldehyde. And then 4 carbons is butyr, or butyraldehyde for butanal, right? I am perfectly fine with you staying with the IUPAC names because they're a lot easier to remember, right? So let's name some ketones, right? Let's name some ketones. Or actually, I'm sorry. There's an example here. Let's try to name this guy right here. So this is the same naming convention as all the other organic compounds we did before, right? We always start with the oxygen or the alcohol or whatever, where that is as number 1 or the closest to it. So that's carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. Sorry, that looks like a 6. That should be a 4. There we go. So we have a aldehyde here at carbon 1, right? And we have a methyl group here at carbon 2. So how do we name this? Quite simply, it's 2-methyl, because it's at the second carbon, and it's alphabetical, right? And since it's on the first carbon, you don't have to say 1 at all. It's just pentanal. Also notice too that when you have an aldehyde organic molecule, the pentanal or the aldehyde part has to always be at the beginning, right? Because you can't connect anything else to H. So it's always going to be at the very beginning. So it's understood that the aldehyde is at the first carbon. All right, so sorry about that. Let's go ahead and do some naming for ketones. Okay. Again, pretty simple for IUPAC system, which is E turns into one. It says 1, but really it's pronounced own, right? And so here we have propanone for 3 carbons, butone for 4 carbons. 3 pentanone. Why is it called 3 pentanone here? Because the ketone is at the 3rd carbon now, right? And then 3 methyl cyclohexanone, right? 3 methyl cyclohexanone, okay? Which is 1, 2, 3. There's the methyl group right here. That's why it's 3 methyl. And then cyclohexanone, because the ketone is at carbon 1. And when you don't say anything, it's assumed to be at the 1st carbon, right? We can also do the common names. So here we have dimethyl ketone, also known as acetone. That's what we use to clean our fingernails of nail polish, right? Dimethyl, because there are 2 methyls, and then there's a ketone in the middle, so that's why it's dimethyl ketone. This is pretty simple. Ethyl methyl ketone, ethyl there, methyl there, ketone in the middle. And then this one is diethyl ketone, 2 ethyl groups on either side of the ketone, right? So naming ketones is pretty simple. So what is the solubility or the properties of aldehydes and ketones in water? I did it again. There's an example at the bottom. So let's go ahead and try to name this guy real quick. Okay, let's go ahead and try to name this guy real quick. Again, we start with the 1st carbon. 1, 2, 3, 4, 5. Right? That doesn't look like a 5. Right? We have a ketone at the 2nd carbon. We have a methyl at the 4th carbon. So alphabetically, 4 methyl. 2, because that's where the ketone is. It's not at 1. Pentanone. Right? Pentanone. Now we can talk about the properties of aldehydes and ketones in water. So remember, to do hydrogen bonding, all you have to do is have a hydrogen and an electronegative atom, right? And both ketones and aldehydes have very electronegative oxygens, right? Makes them very electronegative and makes them very susceptible for hydrogen bonding, where the partially positive hydrogen is attracted to the partially negative oxygen from the ketone or the aldehyde, right? See them up here. Right? Since there is that interaction and that there are those hydrogen bonds present, right? Aldehydes and ketones are soluble in water, but it's just like it is with the alcohols, right? Where the more carbons you have, like we get to right here, the more difficult it is for the ketone or aldehyde to dissolve in water. They become slightly soluble. So all the way up into butanone, or butanal, fully soluble in water, right? They're soluble in water. But once you get to pentanal or 2-pentanone, that's when they become slightly soluble. Hexanal and hexanone, 2-hexanone, right? They're completely insoluble in water. So the same kind of pattern as the alcohols, right? The more carbons, the less likely it is going to be soluble in water, right? Less likely. Because the more carbons you have, the more organic it becomes, right? And likes like. And so there's not enough of the hydrogen bonding to overcome the organic nature of the carbon molecules or the carbon atoms, right? The nonpolar nature of the carbon atoms. So what are some important ketones and aldehydes, eh? Well, we already talked about one. That's propanone, which is acetone, right? And then talked about the other one, formaldehyde. Here's I think that's is that a cuttlefish? Or is that an octopus? It seems too small to be an octopus. Pretty sure it's a cuttlefish. Anyway, so formaldehyde there, preserving your dead specimens, Creepy. Very creepy. Okay. And then here's some other very common aldehydes and ketones, right? We have benzaldehyde here, which is actually almond flavored in smell. Almond smell. Vanillin, we already saw before, that's the vanilla. Right? And cinnamaldehyde is actually cinnamon. I don't know how to spell cinnamon, so I kind of just did a little squiggly there, hoping you would know that said cinnamon. So, yeah, that's cinnamon. Some pretty important aldehydes and ketones there. All right, so let's talk about some reactions of, a couple of reactions of aldehydes and ketones. This first one involves a thing called Tollens reagent, right? In Tollens reagent, and also known as the Tollens test, Tollens reagent only oxidizes aldehydes and not ketones, right? So that's how you can tell the difference between an aldehyde and a ketone. You can also use spectroscopy too, but we'll talk about that later. But if you just want to do a quick test to see if one is a ketone or one's an aldehyde, you can do the Tollens test. It contains silver ions, right? It reacts and oxidizes only aldehydes, not ketones. And in this reaction, ethanol reacts with the Tollens reagent that has the two silvers in it, right? The two silver ions in it. Oxidation occurs. Those electrons go over to the silver, making it a silver mirror, as you can see in the picture right here. And then you get ethanoic acid, also known as acetic acid, which is vinegar, right? And this is actually how they used to make mirrors. Very simply, this is how they used to make mirrors. Pretty cool. Another ketone test. Aldehyde ketone test, right? Is the Benedict's test. So in Benedict's test, there's copper. The Benedict's reagent, there's copper ions, and it forms into brick red solid copper oxide as a positive test for many sugars, right? As a positive test for many sugars. How does it do that? Well, it's because it reacts with this aldehyde right here, right? It reacts with this aldehyde. It oxidizes it to a carboxylic acid, and you get copper oxide, which is brick red. So that's how you also know you have an aldehyde. The copper turns brick red when there's an aldehyde present. Pretty simple reactions, pretty simple tests. And then we can also do reductions of aldehydes and ketones, right? We were oxidizing before with Benedict's and Tollens, but now we're going to reduce, okay? So for example here, in the presence of a platinum catalyst and some hydrogen gas, propanol or propionaldehyde, right, can actually get reduced into a primary alcohol, right, or propyl alcohol, or 1-propanol right here. So what happened is that this double bonded carbonyl carbon oxygen right there, aldehyde, lost its double bond and became a hydroxyl. So that's a reduction, right? Because you gained electrons and you got a hydrogen. So that's a reduction. Same thing can happen with ketones. So here's a ketone in the presence of hydrogen gas and a nickel catalyst, right? Again, the double bonded carbonyl group becomes a hydroxyl group, making a 2-propanol, or a secondary alcohol, or more commonly known as isopropyl alcohol, which is rubbing alcohol, right? The stuff you use to clean your wounds with, and you when you get the COVID vaccination, they wipe it with your arm with some isopropanol, and then they administer the vaccine. So those are some pretty easy reactions, right? So in these particular examples, I have hydrogen gas, but you can also use uh, sodium borohydride as also a source of electrons too for reduction as well. Sodium borohydride, right? And catalysts such as platinum and nickel, right here, you've seen those before. I've talked about those before. They happen a lot in organic chemistry, right? So let's do a quick example, a couple quick examples. I didn't forget about these examples. Okay. So if I oxidize this molecule to butanol, right, what do I get? Well, remember what happened in the previous reaction when we did a an oxidation, right, of ethanol in the previous slides. We have to lose a hydrogen because that's what happens when you do an oxidation, right? And if you lose a hydrogen, the oxygen is missing a bond now because it always has to have two bonds, right? Unless it's charged. So what does it become? Easily this. So we just made a ketone out of 2-butanol, right? And this is methyl ethyl ketone, right? All right, so we're using Tollin's reagent now. Tollin's reagent is the silver plus, right? It has the silver plus in it. What does that do? Well, that oxidizes the aldehyde here, because we have an aldehyde here. Remember, Tollin's only reacts with aldehydes, not ketones. So when we saw it react before, and you're doing oxidation, you have to, once you've already got double bonds on the oxygen, something else has to happen, right? So now it's a carboxylic acid. Right? And this is actually acetic acid. Or vinegar. And that actually ends this lecture.